Hello and good afternoon to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss a very important concept in operating system that is referred to as scheduling algorithm. So a CPU scheduling algorithm is a framework or a mechanism adhered to by the operating system for allotment of CPU time to the processes that are waiting in the ready queue for execution. Again, I'll repeat it. A CPU scheduling algorithm is a framework or a mechanism adhered to by an operating system for allotment of CPU time to the processes that are waiting in the ready queue for execution. So some of the well-known CPU scheduling algorithms are first come first serve scheduling algorithm, shortest job first scheduling algorithm, priority scheduling algorithm, and round robin scheduling algorithm. So these are some of the well-known scheduling algorithms deployed by the operating systems. Now, before moving on to the scheduling algorithms in greater details, let us try to understand some of the important notions of time associated with a process. The first and the most important notion of time associated with a process is called as the arrival time. So arrival time is the time when a process enters into ready queue and waits for its turn of allotment of CPU for execution. So arrival time is the time when the job enters the ready queue, when a process enters the ready queue and waits for its turn for allotment of CPU for execution. So this is what arrival time is. So the time when the process enters into the ready queue. Now burst time. So burst time is the total amount of time that a process takes for its execution on the CPU. So whenever the process is allotted the CPU, the time for which it utilizes the CPU for performing operation is called as the burst time. So burst time is the total amount of time that a process takes for its execution on the CPU. Now likewise you have exit time. So exit time is the time when a process finishes its execution and makes exit from the system. Again, exit time is the time when a process finishes its execution and makes exit from the system. Now, the next important timestamp is called as the response time. The response time is the time in between arrival and the instance the processor gets the CPU for the first time. Again, I'll repeat it. Response time is time in between arrival and the instance the process gets the CPU for the first time is called as response time. Say for example, the process arrives at time instance 2 and it experiences CPU at time instance 5. So the response time will be 5 minus 2, that is 3. So within 3 units of time, the process gets an experience of the CPU. So that's called as response time. So response time is time in between arrival and the instance of the process, the instance the process gets the CPU for the first time. Now the next notion of time is called as waiting time. So waiting time is the total amount of time that a process spends in the ready queue waiting for its turn of CPU allotment for execution. So waiting time is the total time spent by the process in the ready queue waiting for its turn of CPU allotment for execution. So waiting time is equals to turnaround time minus the burst time. So this is the quantitative notion of quantitative representation of waiting time. So waiting time is equals to turnaround time minus burst time. Now turnaround time. So turnaround time is time in between arrival and the first time the job meets its completion, or the first time to its completion is called as turnaround time. So turnaround time is the time in between arrival and the first time a process completes its execution. So turnaround time can be quantitatively represented as arrival burst time plus waiting time, or turnaround time can also be expressed as exit time minus arrival time. So you can use either of these notions. So turnaround time is equals to burst time plus waiting time, or turnaround time is equals to exit time minus arrival time. So these are some of the important notions of time that are associated with the process. Again, we'll repeat it. Arrival time is the time when a process enters the ready queue and waits for its turn of allotment of CPU for execution. Burst time is the total amount of time that a process takes for its execution on the CPU. Exit time is the time when a process finishes its execution and makes exit from the system. Response time is the time in between arrival and the instance the process gets the CPU for the first time. So response time is equals to time when the process gets the CPU for the first time minus arrival time. Waiting time is the total amount of time spent by the process in the ready queue waiting for the CPU. So waiting time equals turnaround time minus burst time. Turnaround time, so turnaround time is the time in between arrival and the first time the job meets its completion or process meets its completion. So turnaround time is equals to burst time plus waiting time, or turnaround time is equals to exit time minus arrival time. So these are some of the important notions of time that one needs to remember, which are associated with the process. Now let us move on to a very important concept that is called scheduling, that is preemptive and non-preemptive scheduling. So preemption basically refers to interrupting the process of execution or interrupting the execution of a process. So that is what is preemption. So if you consider, so let us consider there are two processes, A and B. Now currently the processor is executing the process A. Meanwhile, the processor is executing the process A. A high priority process B comes in, demanding for allotment of CPU. So here, the first process A is being preempted by a second high priority process B that demands for allotment of CPU. So in such situation, what we need to do is we need to make the process A release the CPU and then assign the CPU to another process B and make process A wait in the ready queue. So this is the way how preemption works. Now preemption may be because of varied reasons. Preemption, one may be because of the priority, as we have talked about. Another may be because of time slice that may be associated with the processes. Say for example, I have 5 processes, and with each processes I have each process in the process set of associated time slice of 2 nanoseconds. So the process will execute for 2 nanoseconds and then release the CPU, and it's assigned to a next process. Again, the next process will execute for 2 nanoseconds and then it will release the CPU. So this particular process repeats. So when a time slice is associated with the process, the process releases the CPU and waits for its next allotment of CPU. So that is the reason why switching may take place whenever preemptive scheduling is done. So here, in case of preemptive scheduling, what happens is that a process switches from running state to ready state or from waiting state to ready state frequently. So a process switches from running state to ready state or from waiting state to ready state frequently, because there is a process that is preempting the execution of the process, so that makes the previous process reside in the ready queue, and then the execution will resume once the execution of the latter process is over. So a process switches continuously between the running state and the ready state, or the waiting state and the ready state. Now here what happens is that the resource that is allocated to the process is released and assigned to some other process. As I've said, it may be because of priority or it may be because of time slice. So because of this, there is a frequent change in the state of the process between ready and executing. So whenever a process is being preempted, the preempted process has to reside somewhere so that we can make it wait for the next allotment of CPU. So processes that are preempted are kept in the ready queue. So the process the process stays in the ready queue until the next allotment of CPU is done. So until unless the process is not allotted the CPU, it goes back to the ready queue. So that's what we have learned in the previous class as well. So some of the examples of preemptive scheduling are round robin scheduling, shortest remaining time first, and priority scheduling, preemptive version. So here we have learned that a executing process may be preempted by another process demanding for allotment of CPU time. So in such situation, a process needs to release the CPU, and it has to wait in the ready queue for the next allotment of CPU. And we have also discussed some of the notable examples wherein we have discussed round robin, shortest remaining time first, and priority scheduling are the examples of preemptive scheduling. Now let us move on to non-preemptive scheduling. So in contrast to preemptive scheduling, in case of non-preemptive scheduling, once a resource is assigned to a process, the resource can be taken away from the process only when the process terminates or process enters into waiting state because it has made a system call. Made a system call and it's waiting for some other allotment of some other resources. So here in case of non-preemptive scheduling, once a resource has been assigned to the process releases the resource only when it terminates or it enters into waiting state because it has made system call. So here switching happens only when the process terminates or process switches from running to waiting state because it has made a system call. This implies the resource once allocated to a process, the process holds the same until it terminates or reaches a waiting state. It implies scheduling does not interrupt a running process and it waits for the process to complete, then it allocates the CPU to some other process. So this is the way how non-preemptive scheduling algorithm works. So here, once a resource has been assigned to a process, the process will not be interrupted or disturbed in due course of execution. The process releases the resource only when the process terminates or the process makes some system call and it enters into a waiting state. Now examples of non-preemptive scheduling are shortest job first and priority non-preemptive version. Now let us discuss the first CPU scheduling algorithm that is called as first come first served scheduling algorithm. So first come first served scheduling algorithm, as the name says, it assigns CPU to the process that has arrived first. So here CPU is allotted to the process that requests for it first. The criteria for selecting or selection of a process is the arrival time. So earlier the process arrives, earlier will be the assignment of the CPU to the process. So the criteria for selection of process is the arrival time. So here the dispatcher selects the first job in the ready queue and the job runs till the completion of its CPU burst. That implies first come first serve is a non-preemptive scheduling algorithm. So the dispatcher selects the job from the ready queue and the job runs to the completion of its CPU burst. Now here, whenever a process makes an entry onto the system, as we have all learned, the process will be placed in the ready queue. So how does it actually happen? So on entry of a process to the ready queue, the PCB of the process, the process control block, is linked to the rear of the queue. So you have a queue of processes that are waiting for allotment of CPU using FCFS. So whenever a new process comes in, then the PCB of the process will be attached to the rear of the linked list pertaining to the ready queue. In the process, consequently, what happens is that the average waiting time under FCFS policy is quite long or considerably high, making it non-optimal and exhibiting very poor performance. So why it so happens is because consider a situation you have 5 tasks A, B, C, D and E. C, D and E, and they are arriving in the sequence A, B, C, D and E. So A is the first task and E is the last task to arrive. And consider a situation that C, D and E are tasks that are to be executed first. These are high priority tasks. But since by the virtue of the scheduling algorithm that the operating system is adhering to, whoso is arriving first will be executed first. So here A, B will be executed, then only C, D and E will be executed. So C, D and E will have to wait for a longer period of time in spite of them being a high priority task. So the average waiting time will be definitely high, very high in case of first come first served scheduling algorithm. So this also leads to a very poor performance of the algorithm. So as we have learned, first come first served scheduling algorithm is non-preemptive scheduling algorithm, where the CPU once allotted to a process will be released until only when the process terminates or process enters into waiting state, because it makes a system call for use of IO devices that may not be available at that particular point in time. So in such situation, the process enters into ready state. So these are the only reasons why a process may release the CPU. Otherwise, in case of non-preemptive algorithm, until unless the job or the process does not terminate, the CPU is not released. So this is a brief description of first come first served scheduling algorithm. So here scheduling is done based on the arrival of the sequence of arrival of the processes. So the first job that arrives in the ready queue is the first one that is being scheduled. So we have also learned that in case of first come first served scheduling algorithm, the average waiting time is very long compared to that of other algorithms, because the processes have to wait for longer period of time. And we have also learned that it's a non-preemptive algorithm, wherein once the CPU has been allotted to a particular process in the in the process sequence, then it will retain the CPU until unless it does not complete its execution, or it makes a system call for use of IO devices, or for example for use of IO devices which is not available. So it enters into a ready state and it will be placed in the ready queue. So this is what first come first served scheduling algorithm is all about. Now let us try to understand first come first served scheduling algorithm with the help of a very simple example. So here I have considered 5 processes A, B, C, D and E, and the arrival sequences A, B, C, D and E. So here what I need to determine is the average waiting time and the average turnaround time. So here we have the CPU time associated with the 5 processes. So the CPU time instances are 6, 4, 3, 5, 7. So 6 with A, 4 with B, 3 with C, 5 with D and 7 with E. So all are arriving at time instance 0, but they have arrived in the sequence A, B, C, D and E. So here A will be executed first, followed by B, followed by C, followed by D, followed by E. So since first come first served is a non-preemptive algorithm, so once a process is allotted CPU, it will be released only when the process terminates. Right? Okay. So now let us create draw a statistical understanding of the same. The way how the execution time or turnaround time and the waiting time is estimated. So here I have listed the 5 processes. So here I have listed the 5 processes A, B, C, D and E. So the CPU time associated with A, B, C, D and E are 6, 4, 3, 5 and 7. So arrival time, all are arriving at 0th instance of time. So start time. So since A is the first job that has arrived, so it will start at 0. So since there is no other process being executed by the processor, so it will complete its execution by 6. So here just see, it will exit the system by 6. So turnaround time, one of the quantitative representation for turnaround time is the exit time minus the burst time, right? Okay, so exit time minus the arrival time. So you have 6 minus 0, so this is 6. So the turnaround time in case of A will be 6. Now likewise, B can start only when A finishes its execution. So B will start at 6 and it will go till 10. So B will exit the system at 10. So 10 minus arrival time 0 is 10. So turnaround time is 10. Now likewise, C will start after A and B. So C will start at 10 and it will go up till 13. So C will exit the system at 13. So 13 minus 0 is 13. Likewise, D is sequenced after C, so it will start after C. So D will start at 13 and it will exit the system at 18. So turnaround time is 18 minus arrival time 0, that is 18. Now likewise, E is sequenced after D, so E will start at 18 and it will go till 25. So it will exit the system at 25. So 25 minus 0 is 25. So this is the way how turnaround time is estimated. So turnaround time is either waiting time plus burst time, or it is either exit time minus arrival time. So here I've taken the notion as exit time minus arrival time. So A will exit the system at 6. B will exit the system at 10, C will exit the system at 13, D will exit the system at 18, E will exit the system at 25. So taking these instances of exit time, I've estimated the turnaround time by finding the difference between the exit time and the arrival time. Now likewise, waiting time. So waiting time is estimated as turnaround time minus the burst time. So waiting time is estimated as turnaround time minus burst time. So turnaround time is 6 in case of A. So waiting time is 6 minus 6. So burst time for A is 6. So 6 minus 6 is 0. So A waits for 0 units of time. Right? Likewise in case of B. So turnaround time is 10. Execution time or burst time is 4. So 10 minus 4 is 6. So it waits for 6 units of time in the ready queue. Now likewise C. Turnaround time is 13. Execution time or CPU time is 3, so 13 minus 3 is 10. So C waits for 10 units of time. Now likewise D, turnaround time is 18, so 18 minus execution time is 5, so 18 minus 5 is 13. So it waits for 13 units of time in the ready queue. Now likewise E, turnaround time for E is 25, so 25 minus 7 is 18. So E waits for 18 units of time. So here the average turnaround time is 14.4 and average waiting time is 9.4. So this is the way how the statistical drawings are made for all the processes in terms of a turnaround time and waiting time. So here we see that the turnaround time is 14.4 and waiting time is 9.4. Now let us create a Gantt chart that represents a reflection of whatever we have estimated. So here S associated with the task basically represents start. So S basically refers to starting time for the task or the process A. So we at time instance 0 we have 5 processes that starts its execution. So AS, BS, CS, DS and ES. So A completes its execution by 6. B completes its execution by 10, C completes its execution by 13, D completes its execution by 18 and E completes its execution by 25. So this is a very neat Gantt representation of the way how the various processes A, B, C, D and E are scheduled. So here this is what first come first serve scheduling algorithm is all about, and the manner how it schedules the various tasks. Now let us go through some of the advantages and disadvantages of first come first served scheduling algorithm. So first advantage is that it's simple, easy to understand and easy to implement. So first come first served algorithm is very easy to understand and it is easy to it's very simple, it's very easy to understand and it's very easy to implement. It is suitable for processes with larger burst time as it is as there is minimal context switching between processes. So here, since it's a non-preemptive scheduling algorithm, so it is well suited for a set of processes that has a longer burst time because it has minimum number of context switching. As no priority is involved, processes that arrive first get served first. So this is another advantage of first come first served algorithm. So whosoever arrives first will be executed first. Now let's go through some of the disadvantages. So the first disadvantage that first come first served algorithm suffers from is stagnation. So here all the processes may, irrespective of their priority, whosoever is arriving first will be executed first. So it may lead to a situation where the high priority tasks remain stagnated in the ready queue. As it is a non-preemptive algorithm, the process will only be released when the CPU, the process will only release the CPU on termination, or it enters into a waiting state because it has made a system call. So this is one of the disadvantages. Now another disadvantage is that it's not suitable for system with short response time requirement. Okay, so it's definitely not suitable for system with short response time requirement, and it exhibits poor performance as a consequence of high average waiting time and unpredictable turnaround time. So these are some of the notable disadvantages of first come first serve scheduling algorithm. So in this particular class, what we have learned about is we have learned about what is CPU scheduling, and we have discussed some of the examples of scheduling algorithm. Then we discussed some of the important notions of time, where we discussed arrival time, burst time, exit time, response time, waiting time, and turnaround time. And then we moved on to distinction between preemptive and non-preemptive scheduling, and we associated examples with the same. And then we moved on to first come first served scheduling algorithm, where we learned about the algorithm in detail, and we tried to understand the way how first come first served scheduling algorithm works with the help of an example, where we created a statistical reference, and then we created a Gantt chart that represented the schedule of the algorithm, and eventually we discussed some of the advantages and disadvantages of first come first served scheduling algorithm. So in the next class we will start with the remaining scheduling algorithms. Till then, have a good day. Goodbye.